Welcome everyone to the Moldex 3D webinar series. My name is Alex Baker from the Moldex 3D North America office here in Farmington Hills, Michigan. And today's topic is improving structural performance of reinforced plastic parts. All right, today's agenda is as follows. We're going to be going over kind of an introduction to reinforced polymers, how we can improve the structural quality or the maybe the anisotropic behavior of these polymers using a fiber filler. We'll go into the fiber orientation theory with Moldex 3D's patented IAR-DRPR formulation. And we'll go over some case studies, some advanced concepts as far as coupling in the solver and other shapes of fibers, and then a little bit of a conclusion. All right, so in general, fiber reinforced thermoplastics are thermoplastics with these rigid fibers that almost act as rebar that you would see in concrete. They allow for a structural rigidity as well as a reinforcement from a shrinkage perspective to allow us to control the mechanical properties and maybe even the warpage in the particular directions of flow or the characteristics of flow of the material. You can see that as the fiber length increases, your strength increases, impact resistance increases, stiffness increases. So lots of favorable properties. And in addition to that, typically, the density of these fibers are a little bit lower than the polymer themselves. So introducing fibers can actually end up lightweighting your part as well. As far as the alignment considerations go, when we're talking about an unfilled material or an isotropic material, typically you have the similar shrinkage, not exactly the same because molecular orientation is going to be a consideration as well. But in an isotropic shrinkage, all three directions, the inflow, transverse to flow, and out of plane, all shrink in relatively the same, to a relatively same degree. But when we introduce these fibers into our melt, now the alignment of these fibers are going to create some sort of rigidity in that fiber aligned direction. That's going to prevent the material from shrinking because these rigid fibers have a lower shrinkage property than the polymer matrix around them. And so the shrinkage in that fiber aligned direction is going to be quite low. And in addition, these fibers typically have more favorable mechanical properties as well. And so your mechanical properties are going to be quite favorable in the fiber aligned direction, which is great. But unfortunately, that comes at a cost because transverse to that, wherever we have the unalignment of these fibers, we're going to have the opposite properties. We have higher shrinkage because there's no rigidity from those rigid fibers. We have no prevention of or no reinforcement from a shrinkage perspective either. So usually end up getting a very low amount of shrinkage in the fiber aligned direction and quite a bit of high shrinkage in the transverse to flow direction. And that will end up creating a warpage. Maybe that looks something similar to this. When you have an anisotropic warpage, the shrinkage in all three directions is not exactly the same.